I think I'll go ahead and the stream is going to start the recording now. So I guess whenever you're ready, Tristan, you can go ahead.
Okay, yeah, it looks like the number of people, the rate at which people are joining is slowing down. So yeah, it's my pleasure today to introduce Meredith Grames, who will be giving her summary of her master's research. She should be finishing up her thesis here in the next few months. And so she's ready to kind of show you what she's been working on for the past couple of years. But before I hand it over to Meredith, I thought I would give a little bit of an overview of a few things about her. So Meredith comes from St. Louis. She joined my group a couple of years ago from the University of Missouri. While she was there, she had an experience working on a NASA Student Airborne Research Program project where she looked at land cover and environmental recovery after wildfires. So pretty, pardon the pun, hot topic these days. She looked at a specific wildfire in California in 2017. And so she had actually, I remember looking at her application, a lot of skills that I think lend themselves very well to the remote sensing field. And I think you'll find from her presentation today that she's applied those skills very well. But just a couple of other sort of notes that she let me know about herself. She, like many people in our department, is kind of blessed with a talent for music, and she plays piano, violin, and mallet percussion instruments. And so I know there's obviously a band, or a few bands probably, from people in the department, and I think she fits right in that regard. And then she also loves cooking, and I think like a lot of us during the pandemic, we've been experimenting with different things, and so I think she's been experimenting with different types of foods, and she put in, the way she put it is with varying degrees of success. So I'm sure there's some interesting stories behind all of that. But anyway, not to take up too much of her time, since she's joined my group, she's been working with me and Aaron Morelli, and I would like to acknowledge Aaron on developing some algorithms for our PREFIRE project. And specifically, she's looking at what kind of new information we'll be able to provide for temperature and humidity retrievals in the atmosphere using our PREFIRE observations. So without any more ado, I'll hand it over to Meredith for her presentation.
Great, thank you for that introduction, Tristan. And now I'm gonna try to share my screen. All right. Can you all see my screen and also hear me?
Yes, I think the only thing you have to do is go into presentation mode. Yep.
All right. There we go. Okay. So yeah, as Tristan mentioned, I've been working on algorithm development for PREFIRE, and my research in particular involves using far infrared measurements in atmospheric retrievals. And I had the privilege of working on this with Aaron Morelli and also Tristan. The overarching motivation behind my research is Arctic amplification of global warming. Increasing temperatures leads to diminishing sea ice in the Arctic, which in turn results in increases in atmospheric moisture. And as a strong greenhouse gas, the additional water vapor enhances this atmospheric warming. This has other impacts on atmospheric processes, such as evaporation and precipitation, as well as cloud formation and maintenance. So that's where the far infrared comes in. Now, there are several different definitions or cutoffs given in literature to distinguish the far infrared from mid-infrared. For this presentation, I'll define the far infrared as wavelengths longer than 15 microns or wave numbers less than about 667 inverse centimeters. So why is this important for Arctic climate? Well, for starters, far infrared radiation is sensitive to changes in atmospheric water vapor, particularly in polar regions where atmospheric moisture content is small compared to lower latitudes. So measurements in the far infrared could help improve our observations of the changing moisture content in the Arctic and improve our understanding of Arctic climate change. In addition to this, the far infrared makes up about half of the outgoing long-wave radiation emitted to space. This is demonstrated in the figure to the right, where the upper plot shows the annual mean all-sky outgoing long-wave radiation from 2019. And the bottom plot shows the estimated fraction of that OLR in the far infrared. And so a cursory glance at this will show you that, that the estimated fraction is around half. And that fraction increases as you go poleward in either direction. So that by the time you get to the Arctic or Antarctic, that the fraction of outgoing long-wave radiation, more than half of it is in the far infrared. Despite this, there's a bit of an observation gap in when it comes to the far infrared. Current spaceborne observations of infrared only sample at wavelengths less than 15 microns when they measure the infrared. So PREFIRE, or the Polar Radiant Energy in the Far Infrared Experiment, will work to close that measurement gap. It involves two CubeSats, which will be in near polar orbits, and will take regular measurements of the far infrared from space at hourly to seasonal timescales. And the goal of the mission is to increase our understanding of Arctic energy budgets and the role of the far infrared in Arctic climate. The instrument making these measurements is the Thermal Infrared Spectrometer, or TIRS. TIRS has a spectral resolution of about 5 to 54 spectral range, of 5 to 54 microns with a spectral resolution of 0.86 microns. And my role in PREFIRE has been developing an atmospheric retrieval algorithm for TIRS, which uses principal component regression. This method, though not as accurate as, say, optimal estimation, is good for giving a quick and computationally inexpensive estimate of the state of the atmosphere. So in developing the algorithm, I came up with 3 primary research questions. The first relates to the initial performance of the algorithm. How does the TIRS retrieval compare to retrievals from other instruments? Second question is, can the retrieval algorithm be improved by use of brightness temperature classification? And I'll get into more about what that is a little later. And the final question is, how does including far infrared measurements in TIRS improve atmospheric retrievals? But before all that, first, how does the algorithm work? As I mentioned before, the algorithm works using principal component regression. It's based on an algorithm that was previously developed for AIRS by Weisz et al. I highly recommend their paper for a good explanation of it, and really thankful for Elizabeth Weisz, who gave me advice on my algorithm. The retrieval itself can be summarized by a fairly simple linear equation, as you can see here. We first apply a coefficient matrix C to this other matrix A, and A is calculated by the residual of our observed radiance from the mean state, multiplied by a truncated eigenvector matrix U. From there, we add back in the mean state, which is this X bar, to calculate our retrieved atmospheric state. The retrieved variables from this algorithm are temperature and water vapor mixing ratio profiles, as well as skin temperature and total precipitable water. And for this presentation, I will be focusing on the first two, which are profile retrievals rather than scalar numbers. The training data, first of all, I needed to train the algorithm. So the atmospheric data I used was from the Seaboard database developed by Dr. Ava Borbas and others. It contains global radiosonde data and has a total of about 15,000 clear sky profiles. I also needed radiance data to match up with my profile data. And in order to simulate those radiances, we needed emissivity values. The land emissivity comes from the UW-IR emissivity algorithm, and ocean emissivity from a model developed by Nolly, Minette, and Van Delst, which determines emissivity at a given wave number based on wind speed and instrument zenith angle. Excuse me. Neither of these methods, however, included far infrared wavelengths, so additional calculated spectra from Huang et al. Were added on to include far infrared in the emissivity spectra. For the purposes of training and testing, every 10th profile was retained for testing. So in total, the algorithm is trained with 14,000 profiles, and then testing was, I used 1,500. And for all of you visual people like me, excuse me, this is a scatter plot showing the location of all the seaboard atmospheric profiles. As you probably already guessed, the blue dots indicate water profiles, while the tan dots are land profiles. I would like to see that we see a lot of clusters in heavily populated areas. And in addition, there's measurements tend to be more dense in mid and lower latitudes. And keep that in mind because it will come up later. To further illustrate the training data, these are measurements, measurement density plots, excuse me, for skin temperature on the left and precipitable water on the right. And here the data has been separated into training data indicated by blue and testing data, which is in the orange. And this is used to illustrate that the training data is reasonably representative sample of the population, and that the testing data is a reasonably representative sample of training data, sorry. We also see, however, there's, and this will come up later, that we see a lot of measurements with warmer skin temperatures and a lot of measurements with fairly low profiles with fairly low precipitable water. To go along with the training profile data, as I mentioned before, we need radiances. So to simulate radiances for our profiles, we put the data along with our calculated emissivities through a forward model. Specifically, the principal component-based radiative transfer model, or PCRTM for short. I'm not going to go into detail about how the model works, but I would like to clarify that the principal component, though the forward model is principal component based, these principal components are unrelated to the principal component regression performed in the algorithm development. The model was just used to generate high spectral resolution radiances from the profile data. And these radiances cover a spectral range of 50 to 2760 inverse centimeters with a resolution of 0.5 inverse centimeters. And this range fully covers the spectral range measured by TIRS. And then apply the spectral response function to these generated radiances to simulate what the TIRS instrument would measure based on the profile data. The algorithm itself is trained using residuals from the training data. So if we take the training data to effectively be a population, these residuals are deviations from the mean state. Here, X is the geophysical state vector, or the atmospheric variables that we want to calculate. And Y is our predictands, or in this case, the spectral radiance. We calculate the eigenvector matrix U from the covariance of our simulated radiances. U is then truncated to a certain number of principal components that we wish to retain. And that number is less than or equal to the number of channels we're measuring. I then add a random noise to the residuals of the radiance, and this is to account for noise that we will inevitably have in our observations. When adding noise, we assume a normal distribution with a mean of 0 and standard deviation equal to the noise equivalent delta radiance for a given wavelength. From there, we calculated the coefficient matrix used in the retrieval. That matrix C, essentially what it does is it relates our atmospheric variables and or changes in atmospheric variables from the mean state to the change in radiance from the mean state. So then we come back to our retrieval equation below. This A test shows our changes in our observed radiances from this mean state. And then by applying our the coefficient matrix, we're essentially saying that if the radiance looks like this and looks one way, the atmosphere must look like this. And then when we add back in the mean atmospheric state, we get the actual atmospheric state based on our observed radiances. But what about you? It's been kind of hanging out here the whole time. What exactly is that truncated eigenvector matrix? I mentioned before that U is truncated based on the number of principal components retained for the retrieval. The number of principal components is based on the root mean square error, or RMSE, for temperature and water vapor mixing ratio averaged over the depth of the column. RMSE in this case is the standard deviation of the retrieval error, so you can kind of think about it as sort of a measurement of precision. Meanwhile, principal components essentially explain variance in the data. The majority of the variability can be explained by the first few principal components. But now I'd like to draw your attention to the plot below here this is a plot of the average temperature RMSE for TIRS as a function of the number of principal components. And though we only might need just the first few principal components, you can see that at these lower numbers, the RMSE is high. So even though we might only need those first few PCs to get an accurate retrieval, the retrievals are less precise when only a few principal components are retained. However, as the number of principal components increases, the RMSE tends towards a constant value. So for the TIRS retrieval, we chose to retain 20 principal components because that's where the line starts to level out and you're not getting additional information or retrieval improvement from adding more principal components. So with the algorithm trained in the retrieval setup, we can actually analyze the retrieval performance. I'll focus on temperature and water vapor mixing ratio, as I mentioned before. Retrieval performance was measured with the root mean square error, or RMSE, and percent difference in RMSE is used to look at used when comparing retrievals. And for each analysis, I'll look at retrieval performance for both globally and specifically for the Arctic. And the results are divided into 3 separate analyses, one for each of my research questions. The first is analysis of the retrieval algorithm as is, which, so the retrieval algorithm mentioned above, which is the bulk retrieval. And then I'll look at how improving the retrieval with brightness temperature classification. And finally, I'll compare retrieval for performance for TIRS with and without far infrared measurements included. So first analysis is the bulk retrieval, and this is answering the question, how does TIRS retrieval compare to retrievals from other instruments? And And the instrument I chose to compare it with is the Infrared Atmospheric Sounding Interferometer, or IASI, which was developed by the ESA, and it's a state-of-the-art instrument for atmospheric soundings. It has a spectral range of 645 to 2760 inverse centimeters with a very high spectral resolution of 0.25 inverse centimeters. If you want to think about it, the two instruments in terms of channels, whereas TIRS has 54 channels, IASI has more than 8,000. So, and so I trained the algorithm separately for IASI, and this time with 200 principal components retained for the retrieval. I'm also going to be comparing the TIRS retrieval to the average profile from all seaboard data profiles, which will kind of act as a benchmark for the retrieval. So these are here we have the temperature RMSE profiles for the global data set. On the left is, the left plot is standard pressure units and the right has log pressure. IASI is in the blue line, TIRS is in orange, and then the seaboard profile data is in the green. And this green line shows the RMSE for the average profile. So it's essentially showing us the standard deviation of the training data or typical atmospheric variability. And this acts, as I said, as a benchmark. We want the TIRS retrieval to be performing better than this line. If we compare TIRS to IASI though, so blue and orange lines, IASI has a lower RMSE, but this is to be expected because of the higher spectral resolution. The fact that TIRS is close to IASI, particularly in the lower troposphere, is encouraging. This is the same plot only for global water vapor mixing ratio, RMSE. Again, qualitatively, we can see that TIRS is performing fairly well compared to IASI, and is well below that, that benchmark value that is shown by the green line. And so now I have the same analysis, but considering the Arctic. Here, the temperature RMSE values are similar for the Arctic as to what they were for global values. The only issue is, I will point out, in the uppermost pressure levels, as you can see on the right-hand plot, where TIRS starts overlapping with that benchmark line. However, I will reiterate, as I've mentioned before, that TIRS does have a lower spectral resolution. So we wouldn't expect the TIRS retrieval to perform as well as at these high altitudes, given that lower spectral resolution. And finally, for the bulk retrieval, we have water vapor mixing ratio, RMSE, for the Arctic. And the RMSE values, especially if you look here below about 400 hectopascals, RMSE values tend to be lower in the Arctic compared to those from global retrievals, and actually around closer to the surface, 1,000 to 900 hectopascals, the RMSE values are halved. So now that we have a general idea of the retrieval performance, the question arises, can these retrievals be improved? And the answer briefly is yes. The method I use for improvement is brightness temperature classification. And it works by classifying the radiances into 6 categories based on measured brightness temperature at the 11.14 micron channel. And once again, this classification method is based on the PCR retrieval algorithm developed for AIRS. We used this particular channel because it's found within a spectral window. And the plot below here shows that it's a scatter plot of channel brightness temperature and skin temperature for each profile. And we see that some variability in brightness temperature at warmer temperatures, we see more variability, and that's because there is some water vapor absorption. And so just when we have warmer atmosphere, there's more water vapor generally. So the instrument's not seeing all the way down to the surface. However, you can see at these lower skin temperatures, the brightness temperature at that channel 10 is really close to that 1-to-1 line. As I mentioned before, the radiances were classified based on that brightness temperature. And these tables show the range of brightness temperatures and the number of profiles in each class for both the training data and the testing data. You'll notice that the training data, the classes overlap. And the purpose of that is to reduce the error that would result from a profile being misclassified, particularly at these warmer temperatures where, as I mentioned, the brightness temperature doesn't always completely reflect the surface skin temperature. The retrieval works the same as before, but this time we just have separate regression coefficients for each individual class. And so we can analyze the improvement in the retrievals by calculating the % difference in RMSE for the bulk and classification retrievals. If there's no improvement, we would see values at the 0 line. Positive values would indicate that the brightness temperature classification results in lower performance, and negative values, which is what we're seeing, indicate that we have improvement when brightness temperature classification is used. For both temperature and water vapor profiles, we see the most improvement with these peaks at about in the mid-troposphere, around 500 to 600 hectopascals. Looking at the upper atmosphere, we see some improvement, though not as much as lower levels. And on average, we saw that globally temperature retrievals improved by about 10%, and water vapor retrievals improved on average by about 8%. Here's the same thing, except this time just for the Arctic. And these results are kind of exciting. We see that if we look at the water vapor mixing ratio line here in the orange, we see that we see most improvement further down in the atmosphere, particularly near surface pressures. And that % difference is it's as high as 40%. Temperature, we also see most improvement in the lower atmosphere, although not as high. The peak change in RMSE is 30%, around 800 hectopascals. And on average, the change in temperature retrieval performance is about the same for the Arctic as it was globally. That average % difference is 12%, but water vapor retrievals improved drastically with an average improvement of 18 to 19%. So finally, I want to answer the question of how does including the far infrared measurements improve atmospheric retrievals? Could we get the same results from TIRS with only mid-infrared channels? So to measure this, I took all of my TIRS radiances and subsetted them so that I only had mid-infrared channels. This left about 11 channels out of 54 with a spectral range between 5 and 15 microns. And then retrained the algorithm both for the mid-infrared only radiances as well as the mid-infrared and far infrared radiances. You'll remember, you might remember I mentioned earlier that the number of principal components retained has to be is always less than or equal to the number of channels. And since there are only 11 mid-infrared channels, I used 11 principal components retained for both sets of radiances, so that we're comparing apples to apples. And I used brightness temperature classification in both retrievals. So similar to with brightness temperature classification, these plots show RMSE percent difference for the global data, firstly, with temperature in the blue and water vapor mixing ratio in the orange. More negative values indicate improved retrieval performance when the far infrared is included. We see peak values in temperature higher up in the atmosphere for the global data set, and with peak improvement of around 25%. And then that peak is lower for water vapor mixing ratio. It's closer to around 600 hectopascals, and with the largest difference being between 15 to 20% improvement. On average, that percent difference was about 12%, 12 to 13% for temperature, and around 7% for water vapor. But looking at the Arctic, we see that these peaks where we're seeing a lot of performance improvement have moved slightly lower in the atmosphere, particularly for water vapor. It's closer to, we have kind of these higher values closer to the surface and at higher pressures, excuse me. And we also see more improvement in retrieval performance with peak values between 30 and 35% for water vapor, and close to 40% for our temperature retrievals. But on average, temperature improves 20%, which compared to the 12% from globally at the global analysis, and water vapor saw an improvement on an average of 15%. So there's a lot of plots, but to summarize, and with bulk retrieval and in this retrieval algorithm in general, we saw that the TIRS retrieval was well within the expected variability, particularly in the troposphere, and retrieval performance was worse in the upper atmosphere for TIRS as well as for IASI. So, by using brightness temperature classification, I was able to improve the performance of the retrieval though. The temperature retrieval saw an improvement on average of about 10% for both globally and in the Arctic. Water vapor saw retrievals improved by about 8% globally, but even more so in the Arctic, and there was most improvement closer to the surface. Meanwhile, when we comparing the mid-infrared only radiances to the mid-infrared plus far infrared, we see that having the far infrared results in overall better retrievals, where temperature retrievals improved by about 13% globally and 20% in the Arctic, and water vapor retrievals improved by 7% globally and about 15% in the Arctic. And obviously the work is never done, and there are still several things I would like to look into. Firstly, adding surface pressure to my predictands. So using surface pressure in addition to measured radiance. And this would be useful for retrievals where surface pressure is very low, in particular, high altitude regions, but also, so, Greenland ice sheet in particular, and in Antarctica, we tend to see very low surface pressures. So this would be useful for retrievals in those regions. Also like to look at how the retrieval algorithm handles clouds. All of these retrievals were for clear sky conditions. And finally, I'd like to be able to apply this research to studying polar climate and polar climate variability, and looking at what we can learn about polar climate from these retrieval measurements. And that is really all I have, and I'd be happy to take questions.
All right, thank you, Meredith. Trying to see, I don't see people. So yeah, okay, I guess go ahead and either type in the chat box or maybe raise your hand if you have a question. Okay, not seeing any right now. Well, I'll ask one while people are kind of thinking. So I'm wondering about, I guess maybe putting two things together, and I don't know if you can speculate on this or not. But in terms of the performance with clouds, and in terms of, you've shown, I think that the algorithm has a little bit of performance in terms of retrieving temperature and humidity in the upper troposphere. I know it wasn't quite as good as the lower troposphere, but I am wondering if a cloud is present, do you think the algorithm would have any capability of retrieving temperature and humidity even when there is a cloud present, but just above the cloud?
Definitely, I think above the cloud. And I know from reading literature, particularly the algorithm used for AIRS, they did find that even with clouds present, they were able to still fairly accurately retrieve variables above the clouds when clouds were added to in cloudy scenes. The other thing I would add is also the far infrared. In the case of optically thin clouds, the far infrared could also be useful for not only identifying clouds that were maybe missed by a cloud mask, but those optically thin clouds can be fairly transparent to the far infrared, so you can still get reasonable retrievals even with optically thin clouds in the scene.
Okay, that would be exciting for PREFIRE. Any other questions for Meredith, or did she just do such a great job that there is no outstanding questions? I'm scanning here. I'm not seeing anything. If I'm missing something, please feel free to speak up. Not seeing any hands. All right. Well, I think if there are no questions, the couple of comments for you, Meredith, in the chat box. I'll thank everybody for joining. I think you did an outstanding job. That was a very clear presentation. And I will wish everybody a good afternoon and see you all later.